Hello, today I will be presenting my work on article number 38, which is about the thermal characterization of biofouling around a dynamic submarine electrical cable. This work is done under the supervision of Ahmed, OULD MOCTAR, Bertrand GARNIER, and Franck. My thesis is a collaboration between GEM and LTeN Laboratory and founded by WEAMEC. The outline of my presentation is contained context and problematic, objective, methodology, results and discussion, conclusion, and future work. As a general information, global warming starts increasing from the Industrial Revolution, and this trend completes up to our days. However, nowadays comes a real threat to humanity and a world facing unprecedented environmental challenges. Thus, the use of renewable energy becomes more important. One of the most important renewable energy is the floating wind turbine due to the steady wind speed and its less environmental impact. One of the main challenges of this floating wind turbine is the electrical connection, where the dynamic cable is a key component in the electrical connection. And any negative effect on this cable, it leads to receive less energy. Moreover, it should be noted that one of the most used hanging configurations is the lazy wave due to its suitability for dynamic cables and its features in lowering maximum tension force, and that's why the buoyancy modules are used. This thesis will concentrate on the least known and most impacting effect on the dynamic power cable, which is the colonization of biofouling, particularly the muscles, which creates a mechanical problematic as previous studies and a thermal problematic, which is not yet done. For the mechanical problematic, when the density of the colonized muscles on the cable increases, then the mechanical stresses in the cable increases as well, which leads to a decrease in the fatigue life of the cable and the buoyancy modules. Plus one, the mechanical stress increases, then the electrical conductivity decreases as well, which leads to receive less energy. On the other hand, for the thermal problem, growth of muscles can modify the heat transfer around the cable, which can lead to increase in the temperature of the cable. And if the temperature of the cable increases, then the mechanical stresses in the cable increases as well. Moreover, an important point shall be taken in consideration that as per IEC standard, the International Electrical Commission, the umbilical cables, which is the high voltage dynamic cables, are dimensioned to remain below 90 degrees in the cross-linked polyethylene insulation system, and the conductor in normal operating conditions to avoid any damage in the cable or to have any electrical loss. That's why it's very important to investigate the growth of biofouling if it leads to increase the temperature of the cable or not. And to do this, first, a thermal characterization of muscles shall take place. That's why the objective of this work is to make a thermal characterization for different types of muscles by estimating the effective thermal conductivity of muscles and the heat transfer coefficient of the water around the muscles. The methodology then is an experimental tube is used to perform a stationary measurement. It consists of an aluminum tube implemented with 5K type thermocouples, and 6 silicon rubber heating elements are implemented on the inner side of the aluminum tube to provide a uniform heat. The 6 heaters are maintained in contact with the aluminum tube using a rubber air chamber with an internal pressure about 1.5 bar. Moreover, a sample holder is manufactured in order to allow the measurement inside a tank filled with seawater immobile. Then, the muscles are spread around the experimental tube and maintained using a steel nut or 1 centimeter mesh, with a uniform colonization as shown on the top left figure. Then the experimental tube with muscles are immersed in a tank with a seawater filled with a seawater, and we impose a power and we wait till reaching the steady state. Then, by knowing the power and the internal and external layer temperature of the muscles and the temperature of the water, and by using Fourier's law and the second law of Newton, the effective thermal conductivity of muscles and the heat transfer coefficient of the water around the muscles are estimated. However, in real case, when muscles grows naturally, its distribution and its coverage will not be uniform around the tube. Thus, we will have a complicated geometry, and due to this complicated geometry, the effective thermal conductivity of different types of muscles and the heat transfer coefficient of the water around the muscles are estimated using numerical method, finite elements, COMSOL multiphysics, to solve the 2D heat transfer equation, and a parameter estimation technique, simplex method, is used to obtain the effective thermal conductivity of the muscles and the heat transfer coefficient of the water around the muscles. For the results and discussion, first we begin with a uniform distribution of the muscles around the tube. The effective thermal conductivity and the heat transfer coefficient of the water around the muscles are estimated with a relative uncertainty not exceeds the 9%. And as shown in the top table, that the effective thermal conductivity for the juvenile muscles is smaller than the effective thermal conductivity of mixed and adult muscles, respectively. The explanation of that is the water porosity in the juvenile muscles is smaller than the water porosity of mixed and adult muscles, where a hypothesis is expected that we have a natural convection in the water porous media. Thus, we are expected that we have a more natural convection in the older muscles, showing therefore a higher effective thermal conductivity. Moreover, it's clearly shown that the effective thermal conductivity occurring here is indeed higher than the thermal conductivity of the water. However, the overall resistance must be compared with that of the convection around the tube in the absence of the muscles. On the other hand, it can be noted from the top table that the values of the heat transfer coefficient of the water around the muscles are high, so its contribution in the overall thermal resistance between the cable and the external water is small comparing the one of the biofouling. Moreover, the relative uncertainty reached 19 to 37%. This important relative uncertainty comes from the position of the external thermocouple and the temperature difference between the outer layer of muscles and the temperature and the water temperature. After the previous measurement, the effect of water circulation in the open pores of the biofouling on the effective thermal conductivity is checked. For this purpose, a cluster of glass beads implemented around the experimental tube and maintained using a steel nut as shown in the top figure on the left. The measured porosity of glass medium is about 43%, and its measured effective thermal conductivity was found equal to 2.4 watt per meter Kelvin, which is higher than the thermal conductivity of water and the glass beads and the glass itself. This shows that there is small circulation of water in porous space, meaning a natural convection, which leads to higher effective thermal conductivity, which confirms the hypothesis which we introduced in our previous slide. In real offshore installations, as we said, the muscles don't grow uniformly around the submarine cable. One reason for that is the non-uniform irradiation by the sunlight. Thus, we are estimating the effective thermal conductivity of non-uniform muscles distribution around the tube and the heat transfer coefficient of the water around them. Results in the table shows that the effective thermal conductivity of uniform and non-uniform colonization has approximately the same order of magnitude. The difference can be related to the accuracy of the measurements and the temperature gradient between the external and the internal layer of muscles. Also, can be noted that the sensitivity of the heat transfer coefficient of the water around the muscles is small comparing to the sensitivity of the effective thermal conductivity of the muscles. This result is coherent with our purely conductive model. A modification of this effective thermal conductivity is expected with the convection effect. Actually, in real application, there is a current flow velocity of water in the system, then the effect of the global heat transfer coefficient of the water around the cable or muscles have to be considered. In our future work, the right boundary conditions taking the convection into account will be considered through the simulation of velocity distribution around the system. In this work, the thermal characterization of muscles biocolonization is performed. It's shown that the effective thermal conductivity of muscles depends on the age of muscles, juvenile, mixed, or adult, which has different percentage of water porosity. Also, it's shown that the effective thermal conductivity of muscles is higher than the water thermal conductivity due to internal convection in the water porous media, the muscles. That's why the juvenile muscles has the smallest effective thermal conductivity since it has the smallest water porosity. Last and not least, in the overall resistance, the convective resistance is small comparing to the convective resistance. This is due to the high values of the heat transfer coefficient of the water around the muscles. For future work, experimental tubes are inserted in the Mediterranean Sea and the Atlantic Ocean to have a natural growth of muscles around the tube, then make the experiment or the measurement in more realistic situation in order to confirm the trend which we get. Also, a modeling of the thermal and mechanical effect of the growth of biofouling will take place, and at the end make a kind of thermal sensor in order to monitor the growth of the biofouling using non-stationary method. Thank you so much for your attendance. Any question?